Some joints see primarily shear forces on the bolts or rivets that join them together. So often when we bolt two plates together, we're trying to prevent the plates from being separated, pulled apart. But there are many common types of joints where the shear loading predominates. And in applications like structural steel and ship hulls, aircraft, outer skins, rivets are often used in place of bolts because they don't shake loose. They're cheap, they're lighter than bolts. Now, they're not as strong as a bolt of the same diameter, and you can't really take a riveted joint apart without destroying the rivets. But you can assemble you can rivet two plates together without having access to both sides of the joint. So we're going to talk about shear joints, which may be riveted and they may be bolted, and we're going to treat rivets and bolts the same way for the purposes of design and failure analysis. Now, if you've never seen a rivet gun in use before, I'm going to show you a little video. This is from YouTube user C. Jane Drill. Insert it there. Okay, pause it right here. What's going to happen is this rivet gun is going to pull this ball down through this tube. Hopefully you can see my little pen cursor there. And as the ball gets pulled through this tube, it's going to widen the tube and essentially create what would be the nut. So right now we'll watch him rivet a couple of plates together. All right. So you take your rivet gun, you put it into the holes that were drilled through the two plates that you're joining together. Here we go. And you squeeze the handle a few times, and what you're doing is you're basically creating that nut on the back of the connection. After you squeeze a few times, you'll hear a snap, and then when you turn the joint over, okay, we'll wait till he's finished here. So we have a very nice, clean, fairly flush rivet head on that side, and on the other side, here it is. Okay, so that little ball used to stick up through here, and this tube used to be a lot thinner. The ball's been pulled down, and now we've widened this material so that it is just wider than the hole, and it's not going to pull out. Okay, what kinds of failure modes can riveted or bolted connections have? Well, if we imagine two plates with tensile loads here, if I have a force P, and if I have a little separation distance E here, I'm going to get essentially a bending moment on that rivet. And that bending moment M is going to be equal to that P times E. But bending is not usually the failure mode we think of, or that typically occurs for rivets. It's usually shear. So we're looking at figure C here. So shear, simply tau, force in the rivet divided by rivet area, right, based on the nominal rivet diameter. So that's failure of the rivet. Diagram D here shows tensile failure of the plate itself. That's going to be normal stress, force over area. Area would be the plate cross-sectional area minus any area because of the holes. Bearing stresses and tear-out stresses have been covered in other videos. For bearing stress, again, the hole will crush, and if this plate has a thickness T, and if the hole has a diameter D, then we're looking at a bearing stress area, projected area, of diameter times the thickness of the plate. Okay, so that's the bearing, or sorry, the rivet pressing into this projected area. Tear-out failure, as before, if we have a distance H from the edge of the rivet to the edge of the plate, and once again we have our thickness T, then let's see, here's a complete view of the rivet hole. Tear-out is going to occur along that plane, which has area, once again, T times H, and then there's going to be another area on the other side So 2 shear areas, each with T times H. So that's where that equation comes from. And if, as a rule of thumb, if you have the rivets or bolts at least 1.5 diameters from the edge, you will avoid tear out. Now, there's a couple of ways that we can induce shear in our riveted connection. So let's say we have what looks like a plate on a structural beam. We've got 4 rivets, A, B, C, and D. And a load of 1,000 pounds is placed a little bit off-center. Now that load is going to create 2 kinds of shear stresses. It's going to create direct shear, and it's also going to tend to want to rotate this beam, and the 4 rivets have to conspire to give an equal and opposite moment. All right, and that moment is going to induce a different type of shear stress than the direct shear. And we'll get to that in a few minutes. Now, one thing about rivets, you don't get much clamping force, so the rivets are going to end up taking the shear. One reason to really put a high preload tension on a bolted connection is you create a lot of clamping force, and that clamping force, maybe it'll create enough friction so that the bolts actually don't get put in shear during a joint like this. So imagine there were bolts A, B, C, and D, and they were really tightened, and you've got a material force Fm, and Fm times friction coefficient is going to give you a friction force which would prevent shearing of the bolts. Now, if the bolts loosen, then the bolts are going to have to take shear. So normally we design these joints so that the bolts are big enough to take the shear load, even if we anticipate tightening them enough that they will not have to take the shear directly. They'll just have to generate enough friction force to give us our equal and opposite reaction moments. So normally, if you were going to have a really nice high-end assembled bolted connection, you might use hardened steel dowel pins to locate the parts accurately. Here we're showing 2 plates, and there's a hole in the dark plate, which is this one here, and there's a hole in the lighter plate, which is this one here. And with manufacturing tolerances, you drill your holes, and they're never going to line up exactly. So maybe you make them a little oversized, so that when you put your bolts in the holes, because the holes were a little bit oversized, even if they're misaligned a little bit, you can still fit the bolt in there. And what happens is when you apply a shear load is one bolt is going to hit its hole before the other bolt hits its hole. So it turns out that in the beginning, not all the bolts or rivets end up taking this shear equally. One will take most of the shear. It may cause local yielding, local bearing failure of the hole, and after that happens, eventually the load will even out among the bolts or rivets. A really elegant way to do this would be you would, first of all, you drill your holes. Step 1. Then you take your 2 plates and you stack them on top of each other. And then maybe you invent some kind of a fixture where you can lay the 2 plates down and they will be very precisely located. Okay, so that would be step 2. And then maybe you would drill and ream to very exact diametral tolerances 2 holes. And then you would tap, sort of a light interference fit, tap some hardened steel dowel pins in there. So now those pins will take the shear load evenly. Okay, they're not in sloppy holes. Then you can put your bolts in the oversized holes. So this would be step 3, drill and insert your dowel pins. And then step 4 would be put in your bolts and tighten them so much that these dowel pins probably don't even have to take the shear. But if the bolts loosen, the dowel pins will take the shear and they'll take it fairly evenly. Now there's a procedure here on page 3 of the notes for sizing rivets or bolts for an eccentrically loaded shear joint like the one that was shown on the previous page. Label the holes, find the centroid of the hole pattern, determine the moment of the applied load about the centroid, and then determine the total shear load F that must be taken by the rivets. So there's a number of steps there. You can come back to this and pause at any point after we do an illustrative example, which will show you how we do the direct shear and the shear due to that eccentric moment that tends to want to rotate the beam that way.